Hey class, I wanted to make a brief standalone video on using the Mars simulator. I think you'll find it a pretty useful tool, not just as a necessity for debugging MIPS programs that you're working on, but also as sort of a learning tool to understand more about the microarchitecture of MIPS and how things kind of all tie together. Where this journey starts is actually would be on Canvas and under the resources page. There's a lot of things listed there for resources under MIPS development resources. These are all great and all. The primary ones would be the actual Mars jar file. That's a useful one. There's a couple links to some actual assembly language programming tutorials, which could be helpful on the periphery. And then the other one I would want you to consider downloading would be the assorted MIPS examples. Um, for this tool, similar to ModelSim, it's really your call whether you'd want to run it on the VDI resources or just natively download it to your own laptop. I have it here up on the VDI, which I'll open in a moment here. You would just download that jar file to a directory. You could start with by downloading those assorted examples to a directory and just opening them up and starting from there. So opening up the VDI briefly here, I have things downloaded. Whether that jar file will open for you when you double click it or not depends on your install settings. On the VDI, if the jar file is located on your U drive or on any network drive, it's not going to open up just by double clicking on it, and that's fine. You can still run it from the command line. So just run Java jar and then the dash jar and then the name of the jar file, and it will open up there, and it'll start to load up here. Um, One thing you'll notice, certainly when you open up any of those MIPS examples, is a pretty common thing in that your textbook code examples in any textbook and in any programming language tend to look a lot more simplified than what a quote unquote real world example would look like, and that's certainly the case for MIPS assembly as well. That there's the textbook, you know, concepts we want to make sure that you understand, but then beyond that, there's just stuff you have to have in your code to get things to run properly in a quote unquote real environment. This is true when mapping to real hardware, and it's also equally true when mapping to a simulator that we have here in Mars. So you will see some things that aren't really mentioned all in the book because they really have nothing to do with um, MIPS architecture. They have to do with intermediate formats for loading memory and for determining where things go in memory and supporting certain system calls to allow you to debug your code a little bit easier. So you actually will see that in the very beginning that this has something of an executable format specified for it that the textbook wouldn't really talk about at all. And the first keyword there is .data, specifying that I want to have some pre-initialized values in memory. In this case, it's a size a variable called size and an array of variable called vals for a set of values. And then my actual code is starting in that .text region. If you ever look at a compiler output, you'll see that kind of thing for labeling your data versus your instruction memory, so that the assembler in this case, or the compiler in the more typical case, knows where to put things. Otherwise, the code looks kind of sort of what you've been learning about in class. Load words, some adds, some branches as we get to that in class. And then near the end, there's some things that also wouldn't be talked about in the book. There's these syscall instructions, and there's two in this example here. And that's something that's really implementation specific. So in this case, the MIPS implementation is the simulator itself. In your case, the MIPS implementation will be that VHDL model of the underlying microarchitectural implementation. And in both cases, we have some flexibility with determining how we want to interface with the rest of the real world here. The Mars simulator defines a number of system call operations that it supports, including in this case, it supports a print call, and the syntax for that or the interface for that is defined pretty clearly in the documentation. We load a value in V0 to specify that we want to have a very specific syscall. It's like a software interrupt to do a print. We actually load the value we want to print out, and then that syscall is going to actually print the value out in the transcript window here. That doesn't correspond to anything from a hardware perspective. It would all be software code, driver, things like that. Similarly, there's an exit call or a halt call that loads 10 into that V0 register, and then in calling the syscall, it knows that the code is ready to run. So we've just opened up this file in Mars. We would then want to go and actually assemble it. And here is where you would get some syntax errors if you had them. And once you've assembled it, you'll see that that connection between what the assembly code looks like and what the machine code would correspond to it. And you can actually see that that hexadecimal encoding of the individual instructions. And Mars has got a lot of features here, and you don't necessarily need to be an expert in all of them. There's a lot of information going on in here. Probably most important for you to start would be to get a good feel for that connection between line of code in my assembly and line or lines of code in my assembled output. In this case, for example, there's a single load word instruction in our assembly code in our .asm or .s file. That's actually a pseudo instruction, and we'll be talking a little bit more about those. That's not a native instruction. There isn't actually a native assembly instruction in MIPS that takes a name of a variable into account for the load word instruction. And there wouldn't be, right? Because that doesn't correspond to anything from a hardware perspective. But the assembler is smart enough to take that pseudo instruction to understand what is meant by that variable name and to convert it to what is actually requiring two instructions, which is loading a value into memory based on an address that gets calculated. That's the second thing you'll see, that once you've gone from textbook code to code that has to work in a simulator or on an actual platform, you do have to be very cognizant of where stuff is being put in memory. Uh, Mars lets you edit that. That's under settings, memory configuration. We generally don't have to mess with those settings, and when we do, I'll let you know what changes would need to be made. But this does let you lay out, as part of the application binary interface, where the various aspects of memory are going to be placed. We don't deal with a lot of these things, but the very least, what is relevant to us is what is our initial program counter value going to need to be? What's our instruction base address? And where should our pointers be for when we're accessing data in memory? And that's our .data base address here. You could go in, you could edit these, or you can change some of the settings there, and then your code would have to be reassembled. The defaults are certainly fine to start. This has some implications when we're implementing it ourselves. What does that first program counter need to start at? That's something that's part of the application binary interface. It's a quasi standard for getting your code to work. But that is why that when we were to step into this code, and that's what this is saying, run one step at a time, we will see that the actual address getting loaded into memory being stored in register 1 here is corresponding to 1001 in the upper bits hex, and then zeros for the rest. That is not an accident. That's corresponding to the very first value in our .data region. We're wanting to load that size variable, which is 10 in our assembly. Size is a variable name. It corresponds to an address. That is the address it corresponds to. The actual value in memory that we can see here is in fact 10. And so as you're stepping through, it's going to take two instructions to do that load word equivalent. We will finally have the value of 10 we're interested in loaded into the S7 register, register 23 here. And we can actually see now that it is actually loaded. And as we step through our code, we can start to make our way through. Before each instruction, you can see what are the values of my registers. After each instruction, you can see what the values are of each register. And when it's time for the code to print something out via one of those syscalls, you'll actually see that result printed in the transcript window under the Run IO tab that we have here. I click that green button for Run to run the entirety of it. If we were to walk through this code and what it's doing, it has a length variable or a size variable. It has a series of just hard-coded values corresponding to an array. And as the name kind of sort of suggests here, we are finding the maximum value of that array in this code. So it's going to be loading, it's going to be looping through and loading through an array and offsetting by the appropriate number of bytes to go through it. It's going to be checking to see, is the current value we've loaded currently the largest one we've loaded so far? If so, it's going to store that as an S1 register. And then finally, at the very end, it's going to print out that value of the S1 register. And that's what's being printed in the transcript window there. So those examples are a pretty good starting point. You could do worse than just copy paste this example for your own code that you want to get working here. I'll be writing other examples throughout the semester. There are a whole bunch of tools that are associated with the Mars simulator that are kind of add-on tools. Um, you don't need to ever use any of these. I do like the MIPS X-ray tool here. That allows you, and I have to connect it back to the simulator. That allows you, as you step through the code, to not only see, as we already do, the values of the software accessible registers and some of the state information. It allows you to actually see information as it's flowing through um, a very high level implementation of a microarchitecture for it. This is somewhat similar to the single cycle processor we're starting to explore as part of the class. It's not exactly the same. You can't take this and be done with your project. We do have to implement all the nitty gritty details, but it does show you that as we are executing this code, um, certainly supposed to, as we are executing this code, um, the values are flowing through it. And you can see, for example, here is the instruction name, here's what their encoding is, and eventually it'll show here's the actual details of information flowing through here. With a decent amount of information of your textbook implementation of what are the values of these control signals as they're getting set, what is happening inside my register file as things are being loaded into it. This is pretty useful for checking your own knowledge base, at least, of for what you are implementing. Is it doing what you're expecting it to do? This doesn't do the project for you, but it can help. It's a nice visual tool, is all it ultimately is, for helping to visualize what is happening inside your processor. That's all I really wanted to talk about today. So, eventually you'll be required to do this for a homework assignment. It's useful to just go to the resources tab, give it a download, check it out, and I think you'll find it's kind of fun to play around with assembly. I'm never going to be asking you to be writing pages and pages of assembly in this class, but as you're working on homework or just trying to understand things in more depth, this is a very helpful tool for either visualizing or just tracing the execution of your assembly code. Okay, well, have fun with that.